All right, an eigenvalue, eigenvector problem. We're going to find the eigenvalues and eigenvectors for this matrix. In this case, they're going to be complex. So it's an example of how to deal with complex eigenvalues and eigenvectors. And it's a good day for complex numbers. So let's do it. This equation looks like 3 minus lambda minus 2, 4, and minus 1 minus lambda. We want the determinant of that. So that's 3 minus lambda times negative 1 minus lambda minus a negative 2 times 4, which ends up being lambda squared. We have plus lambda minus 3 lambda, so minus 2 lambda. And then we have minus 3 plus 8 is plus 5. So that's our characteristic polynomial for the eigenvalues. We want to set that equal to 0. In this case, we cannot factor this. So normally we would factor it if possible, but we can't factor it, so we use the quadratic equation. 2 plus or minus the square root of 4 minus 4 times 5 times 1 over 2. This looks like 2 plus or minus the square root of negative 16 over 2. So that's 1 plus or minus 2 times I. Square root of 16 is 4. 4 divided by this 2 gives us a 2 times the I. So we have 1 plus or minus 2I. The eigenvalues always come in complex conjugate pairs like this. So we're expecting 2 eigenvalues, and we have 2, and they always come, like I said, in pairs. So with that, we want to now take lambda equals 1 plus 2I and find the corresponding eigenvector. So the eigenvector equation, remember, is A minus lambda I times V equals 0. So for us here, that is 3 minus 1 plus 2I. We have a negative 2, a 4, and a negative 1 minus 1 plus 2I times V1, V2 equals 0, 0. That is 3 minus 1 is 2, negative on the 2I, right? This negative sign carries across both of these two terms. Negative 2, we have 4, we have negative 2 minus 2I times V1, V2 equals 0, 0. So there's our system of equations for the eigenvectors. We are just about done, but I'm going to clear out a little bit of space for the work, and then we'll finish this problem. I left our system of equations for our eigenvalues up on the board. This is what we have. So let's do the matrix multiplication on that. That looks like 2 minus 2I times V1 minus 2V2 equals 0. The two equations look different now with complex numbers. They are still equivalent. If I multiplied the second line through by the conjugate, minus 2 plus 2I, what I would get is a line that was a multiple of the first one. So the two equations are still equivalent. I don't have two equations for the two unknowns. I just have the one, which, is nice. So this looks like 2 minus 2I times V1 equals V2. And now I pick a value for V1 or V2. With the previous examples, it didn't really matter if I pick a value for V1 or V2. Now with the complex numbers, I just want to pick a value for V1 so that I can see exactly what V2 is. So let me pick V1 equals 1. Then V2 looks like it's going to be, if I have a 1 in here for V1, and if I divide through by 2 to solve for V2, I get 1 minus I. So we have lambda equals 1 plus or minus 2I as the eigenvalues. And the corresponding eigenvectors are, if V1 is 1 and V2 is 1 minus I. The eigenvectors also come in conjugate pairs, just like the eigenvalues. So if I know I had the 1 plus 2I corresponding to the vector 1, 1 minus I, then I know the other eigenvector is just going to be the complex conjugate. So I can just put the minus plus on I When this one was a plus, 1 plus 2i, this one was a minus, 1 minus I, which is why it's a minus plus here instead of a plus minus. I'm just getting these terms to agree and to go along with each other, right? But it is nice that they only come in pairs. I don't have to do this process twice. I only have to do it once. I did it for lambda equals 1 plus 2i, and then I get both of the eigenvalues. I just get the one that comes along with it, and then I can take the conjugate, just put a plus minus or minus plus, whichever one corresponds, and then I have my second eigenvector. So I get both of them, kind of 2 for the price of 1 when it comes to complex.